Hello everyone, here we are in part 2 of module 1, and we're going to continue with our discussion of process diagrams and define some more terms as part of this first module. So last time we had ended in the last lecture on process diagrams, and we had ended with the definition of a process diagram being that a process is any change that a system undergoes from one state to another. And the path to that process is a series of states through which a system passes. So if we draw a process from 1 to 2, it would have some sort of path that looks like this, as defined last time between point 1 and point 2. So to continue from the discussion from last part and from part 1, we can actually define different types of processes as some processes are going to be called iso processes. And what we mean by iso processes is processes where a property remains constant. And in this class, we're going to go over a few of the different iso processes. So one iso process is going to be called an isothermal process, which you might have heard of before. And an isothermal process is when temperature remains constant. We're also going to be looking at isobaric processes. Isobaric is when the pressure stays constant. So we have a constant pressure. And we're also going to be looking at isochoric processes, which would mean constant volume. So there's going to be different types of processes we're going to be looking at, and they're going to be defined as either processes that change everything, so they can change volume, pressure, and temperature, but some of these processes might have a property that remains constant, and that's the definition of an iso process, is when one property remains constant. Okay, and those are 3 examples. Now, we're also going to want to define a cycle. A cycle is when a system returns to its initial state at the end of a process. So a cycle would be defined as something like this. So if we have a PV diagram, and we have our process from 1 to 2, a cycle would be defined as a process from 1 to 2, and then a process from 2 to 1 going back to 1. So it completes a cycle. So we can say the system returns to initial state after a series of processes. And we can also write that because we need more than one process to complete a cycle, we can say that 2 or more processes create a cycle. So I'm not going to write this, but you could have a path A and a path B, for example. So path A going from 1 to 2, and then path B going from 2 to 1 to complete that cycle. Now, a little bit more definitions for today, as we are going through a lot of definitions to sort of bring everyone to speed with the terms we're going to be using for this class. So the next definition we're going to go through is a pure substance. And what is a pure substance in thermodynamics? Essentially, a pure substance is one that is uniform and invariable in chemical composition. So it's a substance that is uniform and invariable in chemical composition. And we can also say that it can exist in more than one phase. So if you remember what the phases are, you'll know that it can exist in more than one phase, meaning it can exist in, for example, as vapor, as liquid, or as solid, all at once. Okay, so it can exist in more than one phase at once. We also can think of, in this class, we can think as air as a pure substance. For this class. And the reason I bring this up is because air is made of a mixture of gases. However, it is a pretty uniform mixture of gases. So we have 79% nitrogen, 21% oxygen, and the mix of the air is considered pure in this class because it stays a gas and does not really react. Okay, but we will go over when air can be treated as a pure substance and when air cannot be treated as a pure substance. So we'll go into that a little bit more. Now, next definition is equilibrium. And again, we're defining a lot of terms today to be able to move forward throughout the class and understand what we're talking about throughout the class without having to define terms later on. So, equilibrium means that the values of all the system is the same for all its properties. So the values of all the system is the same for all its properties. And what we mean by that is that, for example, in our class, if we have a piston cylinder assembly and we have some air inside a piston cylinder, if we heat it from the bottom, we're going to assume that the air, so the whole air, heats up uniformly. Okay, so it doesn't mean that this particle of air here is going to be hotter than this particle of air here. They're all going to be the same temperature. Okay, and that's really important. So we have essentially a system that behaves as a whole and not as points inside the system that are at different temperatures. So essentially within our system we have what is called equilibrium balance. And we have different types of equilibrium. So we can talk about the different types of equilibrium that we're going to look at. So one of the types of equilibrium that we have is mechanical equilibrium. And mechanical equilibrium means that there would be no change in pressure, for example. So if there's no change in pressure in our system, we know that our system is in mechanical equilibrium. If there is no change in temperature, we know there is no change in thermal equilibrium. And this equilibrium can obviously change if we have a change in the system over time. But everything changes slowly and goes from one equilibrium to another. Okay, so we essentially go, if we're heating up air, we go from the whole mixture of air going from, for example, 25 degrees Celsius at time 0, and then at time 100, so let's say 0 seconds and 100 seconds, now our mixture is at 50 degrees Celsius. But it's uniformly at, the whole mixture is uniformly at 50 and at 25 degrees Celsius. Okay, there's also chemical equilibrium, which talks about chemical composition. And there's also such a thing, which we're not going to be looking at much, but there's also phase equilibrium, which is the equilibrium that deals with the change of phase. So the mass of the phase, or the mass of the phases, stays the same when we have equilibrium. So let's take an example of, we have water inside a piston cylinder. Okay, we have water here. And we have 25% of the water at the bottom here is liquid water. And 75% of the water in green is gas. And sorry, I should have put that in green. Let me put it in green. So 75% of the water is gas, or also called vapor for water. And we have this mixture that's liquid and water, and we said 25% and 75%. If this mixture does not change, we have phase equilibrium. Now, over time, if you start heating this water more, so if you add heat to the water, what's going to happen is the gas might go to 100%. And liquid will become 0%. And there we see that we have a change in phase equilibrium that's going to happen slowly. Okay? Now, in our class, we're going to be looking at states of different equilibrium that change very slowly. So essentially, we're not going to be looking at transient changes in temperature, which means we're not going to be looking at very quick changes in temperature. We're going to be looking at very small changes that happen over time, and those changes occur, and once they stop in time, they create this new equilibrium. So for example, from going to 25% liquid to 0% liquid, it will happen slowly enough that we can capture that change. And that change is actually called quasi-equilibrium. And we can also think of it as quasi-steady state change. So what that means is that all properties change slowly along the path line. So from one state to another, we have a change happening slowly. And the best example of this is to look at a specific problem that we could have in our class, and how we're going to analyze the problem versus how it might actually happen in real life. So if, let's say we have a piston cylinder assembly, and this piston cylinder assembly has air at the bottom filling it up, and we also have these stops up here that are going to stop the piston from moving higher than this. So this is the highest position of the piston. Okay, these are called stops, and we're going to be talking about them throughout the class so we can learn about them. And on here, we're going to add little blocks that have a certain mass. Okay, we're going to add 4 blocks with a certain mass. Now, what happens if we look at a PV diagram now? What happens if we take out, so let's say we have point 1 is here with our point 1 with a high pressure and a low volume, so P1 and V1. So the pressure inside would be P1, and we have a certain volume, which is pretty small. Okay, the volume is smaller than if the piston cylinder was moved to here. Obviously, we would have a bigger volume, right? The volume inside would be bigger. Okay, so the idea is we start at point 1, and then we say, what happens if we take 1 block off at a time? If we take 1 block off at a time, this process is going to go from 1 to 1B, for example. Okay, we're going to take out this block. Then we're going to take out a second block in green. And then this process is going to go from 1B to 1C. And then we're going to take out a third block. And then this process is going to go from 1C to 1D. And then finally, we're going to take out the last block. We're going to highlight it in white. And we're going to go from 1D to 2, and we're going to complete our process. And throughout this process, when you take out blocks off from a piston cylinder, what happens? The piston starts moving up until it reaches the stops. So this would be volume 2 when it reaches the stops. Okay, so that's usually when you take off block by block. You can think of that process as a quasi-equilibrium process. What it means is that the process happens slowly, where you take out 1 block, another little by little, and you can find the path that is happening throughout while the piston reaches a new equilibrium. So if you had 3 blocks left, for example, if I redraw my piston cylinder assembly here, if you had 3 blocks left, you would move up a little bit to a new equilibrium. And then you would move up one more time when you have 2 blocks left. You would move up to a new equilibrium again. And etc., etc., etc. So you're going through different equilibriums where you can stop pretty much. And that's how we're going to analyze our problems in this class. Now, a non-equilibrium approach to the problem would be to say, what happens if we take all the blocks off at once? What happens? If we take all the blocks off at once, we have a problem because our pressure is now not uniform because we're going too fast, and piston moves up very fast. And it's very hard to analyze mathematically if we take out all the weights at once, all the little blocks at once, because now we have an unstable system. We don't really know, it doesn't really have time to come to equilibrium. So in this class, we're going to be using the quasi-equilibrium approach, which is we assume that all changes are slow enough that we can capture the equilibrium along the path. Okay? And we can call this, a quasi-equilibrium system. Now, we're also going to be looking at, in this class, steady flow processes. And we're going to define what a steady flow process is. Steady flow process and transient process. And we'll go over those a little bit later in the semester. But essentially, what a steady flow process means is that we have no change with time. So for example, an example of a steady flow process would be flow going through a pipe. We have a certain mass flow rate, m dot, going in. Okay, m dot is mass flow rate. And we have a certain mass flow rate coming out, which would be the mass flow rate coming out. And over time, this mass flow rate does not change. It's always turned on, and the mass always goes in through here and always goes out through here with the same steady flow. So that means that if we calculate how much mass at any point in time there is within this little control volume, so remember this is our control volume. If we find out what our mass is in our control volume, we find out that the mass in our control volume is equal to a constant. It's always constant because it's always being fed by new mass flow rate coming in and mass flow rate going out that is equal. And that also means that the energy inside the control volume is also constant. And we'll look into that a little bit later into the semester as well. So the mass is constant and the energy is constant as well. Now a transient process is the opposite of that. So a transient process is a process, for example, so let's look at a different type of process, which is a transient. So try to think of some examples of a transient process. So one example would be to have filling up a bathtub. So if you fill up a bathtub, you have your sink or whatever with your water coming in, and you're filling up this tub with water. So you have water coming in, and you're filling this up. Over time, this is going to increase the amount of water. The mass in, there's going to be mass in and there's going to be no mass out, for example. Which means that overall, our mass and our control volume, let's assume that our control volume is this control volume right here. The mass of water in the control volume is going to go up. Okay, and that also means that the energy could go up. Another example of a transient process would be, so let me just cut this off here. So another example of a transient process would be leaving a hot tea with surroundings to cool. So now we have a hot tea. Okay, so let's say we have a hot tea inside a room that's, let's say, at 20 degrees Celsius, and our hot tea is at 100 degrees Celsius. And our hot tea is going to have some energy going out to the 20 degrees, and it's going to cool down over time. Now, the energy in our control volume is going down. The energy in our tea is going down, and the energy is actually filling up the surroundings. Okay, so those are two examples of transient processes. And we're going to be looking at the two different types throughout our class. So this will be really important. We're going to be looking at the two different types throughout the class. So moving forward from this, just a few different things in terms of units and looking at pressure, volume, and temperature, just to summarize for everyone what we're going to be doing throughout the semester. The units we're going to be using as SI units for this class are the following. So we have units for mass, length, time, and force that are going to be extremely important throughout. And mass will be done in kilograms, of course, as our SI. Length is in meters, time will be in seconds, and force will be in newtons. And we can also write that 1 newton, just to define what the newton is equal to 1 kilogram multiplied by meters per second squared. Now, why is that? That is because F is equal to MA. Okay, and by using the units of MA, you can find what the unit of the Newton represents. Now, remember that mass is not the same thing as weight. Weight is equal to mg, and it's equal to mass times 9.81 meters per second squared. Okay, so weight is also in newtons, just to make sure we don't confuse weight and mass. Okay, now volume is going to be in meters cubed as our SI unit. And in this class, we're also going to be using a unit called specific volume. Okay, and specific volume is a little v. So volume is a big V in this class, so we're going to be using a big V as the symbol for volume. Okay, and we're going to be using the small v as the symbol for specific volume. And specific volume is equal to V over mass. So it's the volume divided by mass. Anytime you have the word specific in front of something, it means usually that it's divided by the mass. Okay? And what's really interesting about that is that the specific volume is actually the inverse of something else that we know about. So let me talk about something else that we already know about, and that other thing is density. And we know that density is defined as rho, so the symbol for density is rho, and it's equal to m over v. It's the mass divided by the volume. It's the amount of mass you can pack in a meter cubed, for example. So the more density that you have, the more weight you have within the same meter cubed. Okay, if you look at the two equations here, you can see there's a similarity. You can see that specific volume is equal to 1 over the density. So if you can find the density of something, you can find the specific volume of something, and vice versa. Okay, another useful trick to have in some of the questions that we're going to follow throughout the course is the conversion between liters and meters cubed. So 1 liter is equal to 10 to the minus 3 meters cubed, which is also equal to 0.001 meters cubed. This will be useful when you're solving problems with liters sometimes. Could be useful. Okay? And that covers volume. And now we're going to be talking about pressure, and then we'll talk finally about temperature at the end of the lecture. So pressure is next. What about pressure? So pressure is defined as what? It's defined as the normal component of force over a unit area. So it's the normal component of force over a unit area. So essentially, pressure is equal to force over area. Okay, and the pressure is usually defined in pascals. Okay, and pascals is equivalent to newtons per meters squared. So if we define pressure per unit area, we have a certain area where the force is being applied, and a force would be applied on that area, and that is the equivalent of the pressure. Okay, so it's important to talk about that. Now, pressure is used in fluids and gases. In solids, we actually use a different term than pressure. We use stress for solids. So pressure is turned into stress for solids. And the definition is a little bit different. Now, in our class, we usually use kilopascals for pressure because pascals are very, very small. So it turns out that pascals are a very, very small unit of pressure. So for convenience, we usually use kilopascals as the main unit for pressure. But we do have to be careful when we're computing problems. We have to make sure that we're keeping with our units. So if we use kilopascals, it essentially means that we're using kilonewtons per meter squared. And so we have to keep that into account if we're computing the pressure from force and area. We have to make sure we keep our units correct. Okay, and just a few little other things that are used as units. You can use atmospheres for pressure. And so 1 atmosphere is actually equivalent to 101,325 pascals. And 1 bar is equivalent to 100,000 pascals. So that's another unit. 1 bar is equal to 100,000 pascals, which is equal to 100 kilopascals. So you could be faced with all these units, but we're usually going to try and keep it to pascals or kilopascals. Now, in thermodynamics, we usually use absolute pressure. And what we mean by absolute pressure is that the pressure is measured from the absolute zero pressure. So absolute pressure is measured compared to absolute zero pressure. So it's the total pressure used. Now, in real life, the pressure is measured by the difference in absolute pressure and atmospheric pressure. So in real life, we have a constant pressure on our Earth. And that constant pressure is called the atmospheric pressure. And the atmospheric pressure is usually always around 1 atmosphere, which is 101,325 pascals. So in real life, pressure is measured by the difference between absolute and atmospheric, because it's a lot easier to measure. If we know everything is at atmospheric pressure, if we set a 0 at atmospheric pressure, then we can use a pressure gauge, for example, that will measure the difference between the atmospheric, which is its 0, and the absolute pressure, which would be the change from atmospheric. Okay, and that's called the gauge pressure. Okay, so if we look at a graph of pressure in general and how we measure pressure as a whole in thermodynamics, we can sort of summarize it in the following way. So if we have, let's say this is a pressure graph and we have some sort of depth to understand what's happening. So it's just a pressure graph and we're going to have different values lined up on it. So this would be pressure atmospheric. And we're going to be measuring two different points, which is going to be this point and this point. Okay, so we're going to be measuring two different pressure levels. So this pressure level would be from 0, so this is 0. From 0 would be P atmospheric, so we would have P atmospheric plus this P gauge, right? So P gauge would measure the difference between atmospheric and absolute. And this whole line here would be pressure absolute. So the whole way up would be pressure absolute. Okay, in thermodynamics, again, we're interested in the absolute pressure. But sometimes we're going to be given the gauge pressure and we have to convert it to absolute pressure and vice versa. Okay, now if the pressure, and this is a little bit of an engineering difficulty because different engineers had different ways of doing things and they decided that the standard was this, but if the pressure is above atmospheric pressure, they call it pressure gauge. If the pressure is below atmospheric pressure, they call it P vacuum. So they call it P vacuum, okay, if the pressure is below. And so now the absolute pressure would be up to here for this reading. And our P atmosphere would still be all the way to the top. So now, when you have a pressure that's lower than atmosphere, so essentially it's lower than the atmospheric pressure, you actually call that a vacuum pressure from the reading of atmosphere. Okay? So we can summarize that if the pressure is higher than atmospheric pressure, we have this following equation, that pressure gauge is equal to pressure absolute minus pressure atmosphere. And if we do have a vacuum, so the pressure for a vacuum would be equal to P atmosphere minus P absolute. And you can refer back to this diagram if you're confused about this, but we will be mostly dealing with pressure gauge, and most of the time we'll be actually getting all our values in pressure absolute, so it shouldn't be too much of a problem. So just remember this, whenever it's not specified, pressure is always absolute. Okay, so if in a question you're given pressure, you just assume that the pressure is the absolute pressure. Now, as an example of pressure gauge, when you have a tire pressure and you go measure your tire pressure at a gas station, if your tire pressure reads 32 psi, its actual pressure is 32 psi plus atmospheric pressure, which turns out to be around 14.3 psi. So a 32 psi reading of your tire pressure is actually a 46.3 psi pressure inside the tire. Okay, so that's something good to know. Okay, so that there is a difference between gauge and absolute. But in this class, we will be using absolute except if it's told that it's something else. Okay, the next thing I want to look at is pressure in terms of, so variation of pressure with depth. And pressure varies with depth in the following way. So we can say that in a fluid at rest, pressure does not change in the horizontal direction. Okay, so the first thing we can say is that in a fluid at rest, pressure does not change in the horizontal direction. Now, in the vertical direction, pressure increases in depth as a result of added weight of the fluid. So essentially, if we're looking at the pressure at a certain depth in, let's say, a fluid or a water tank, the deeper we go, the more pressure there is. And the reason is because we have more weight above the fluid at that point. So let's look at a rectangular fluid element of height z and length x and unit depth. So let's say that we have within a water tank, okay, we have a rectangular fluid element and that fluid element has a height of delta z. Okay, so we're going to call that height delta z. It's going to have a length delta x and unit depth. Now, what I mean by unit depth is that essentially delta y, which would be into the paper or into the screen in this case, would be equal to 1. Okay, it has a 1 depth. Okay, it has a depth of 1, so the depth doesn't really affect anything. And so if we draw this rectangular element, so I'm going to draw it here on a graph on a zx graph, because we know it has unit depth, so we can look at it just from the z graph. If we look at the graph itself, and we take this element is said to have a height delta z, so delta z is going to be the height. It has a width delta x, or length of delta x, and it has a certain weight. This rectangular element of fluid has a certain weight, and that weight is pulled by gravity, so it's pulled down by gravity. Okay? And around this box, we have pressure from all four sides from the rest of the fluid. So think of this box of fluid, or this element of fluid inside like a water tank. Okay, and the pressure around that fluid, that imaginary element, is going to have pressure coming from all four sides, keeping it in equilibrium. And it's going to have a pressure 1 pushing up, a pressure 2 pushing down, and it's going to have also pressures on the sides, but those pressures on the sides are going to cancel out. So the pressures in the x direction are going to cancel out because there's no weight being pushed from left to right. The weight is straight down because of gravity. So we can say that gravity is going down essentially. Okay, so now what happens if we take a force balance on this? So kind of like a statics analysis, a force balance in the z direction. What happens if we take a force balance in the z direction? Well, we can say that the sum of the forces in the z direction are equal to 0 because of the fact that it's in equilibrium. Okay, so it's in equilibrium. So our force balance is 0. And we can say that the force in z is equal to the mass times the acceleration in z. Just replacing what z would be equal to. So now let's look at the forces in the z direction. So try to do this by yourself before looking at my solution, but try to do the sum of the forces in the z direction. So one of the first forces in the z direction is going to be this pressure 2 element. Okay, and pressure 2, remember pressure is equal to force over area. So now we have pressure 2, sorry, let me write it in white. We have pressure 2 times delta x times delta y, but we remember that delta y is a unit, so it's just going to go to 1. Okay, so I'm going to erase this and make it just equal to 1. So I'm going to make it disappear because it's just 1 times p delta x minus p1 times delta x again, and then minus rho g delta x times delta z. Now, where does this come from? Where does this term come from? This term comes from the fact that the weight is equal to mg. So, if you remember correctly, mass times gravity is the same thing as, what's the definition of density? So if you know the definition of density, it'll make sense. So the density is rho times delta x times delta z times delta y. So essentially mg is equal to rho times the volume. So it's the density times the volume is equal to the mass multiplied by g. And so we get that this whole term is equal to 0. And now we can now write that delta p, or p2 minus p1, by just rearranging the equation and getting rid of the x's because it's equal to 0. So we can get rid of the 3 x's because we can just divide both sides by delta x. So we have p2 minus p1, and we bring the rho gz to the other side. And we have that p2 minus p1 is equal to rho times g times delta z. Okay? And remember that the rho is the density, okay, not the pressure, it's density. And so we have that as our equation. And we can conclude that the pressure difference between 2 points in a constant density fluid is proportional to the vertical distance. So we can say that delta P from our equation is directly proportional to density and to the change in height. Okay? And we know that gravity does not change, so it's always going to be the same. Okay, So the reason why we did this is to talk a little bit about density and when can we assume that density is essentially okay to be assumed as constant. So when can density be thought of as constant? So density can be thought of as constant for liquids. And the reason why is because liquids are usually incompressible. It takes a huge amount of force to make a liquid compressible. So liquids are usually incompressible. So if you try to compress water in its liquid form, it's going to be very hard to do. You can change the shape of water, but it's very hard to compress. Okay? Now, you can assume that the density is also constant for gases if delta Z is small. So let's say you're looking at the density in a gas inside a room. So let's say we have air inside a room. If you're looking at the density of air next to the ceiling or next to the floor, inside a room, the density of that air is usually going to be very similar. Okay, as long as the temperature is the same, it won't make a big difference in density because there's not much difference in height. Now, if you look at the difference in density of air between the air on the surface of the Earth and then air 10,000 feet in the air, there's a big difference in density. Okay, the density goes a lot lower when you go up much higher. Okay, so it's only okay for gases if delta Z is small. And we cannot also think of density as constant if there are big temperature differences. So I'm putting no. So this would be yes and yes. Okay, we can consider constant. And here it's no. So no if there are big temperature differences. Okay, if there's a big temperature difference between point 1 and point 2 or between time 1 and time 2, the density of the air is usually going to change a lot. And number 4 is you cannot assume that density is going to be constant if you look at liquids at great depths. So if you look at great depths at some liquids, the density is going to change a lot because of the fact that there's so much weight above just above the liquid in general. So we can also, we have this final equation that says that delta P is equal to rho G delta Z. And we can rearrange this equation to say that delta Z is equal to delta P over rho G. And the reason we want to rearrange this equation is we can actually rearrange this equation like this. And you might have seen this in physics, or you will see it in transport phenomena course if you are taking it as well, that we can measure delta P. So delta P by looking at the height of a fluid in a column. So it's very interesting, but we can actually figure out what the pressure difference is between two systems or two different parts by just looking at the height of fluid in a column, and we'll be looking at that in part 3 of we're going to be looking at that in part 3 of our Module 1 lectures. So we're going to stop it here for part 2, and in part 3 we're going to be looking at how we can measure pressure, and then we'll go on to temperature. Part 3 will be a little bit shorter than part 2, and it'll conclude Module 1. So see you in part 3.